Hello everyone, welcome to the combinational and sequential design practical series using SimulIDE. So today we'll be doing the implementing of code converters. We'll be doing this four circuits. The first is to design and implement binary to gray code converter, then gray to binary code converter, then binary to BCD, and finally binary to XS3 code converter. First I will explain each and every code converter, and then we'll implement using SimulIDE. So first let us start with the binary to gray code converter. Before starting with this, we must know the conversion process. So how this conversion takes place. So suppose if we have a binary code, say we have 1001. Now how to convert this 1001 binary code to gray code? So the process is very simple. The first number, the leftmost bit, we write as it is, and then what we do, we add the first number 1 with 0. So 1 plus 0 is of course 1. Then to get the next bit, we add 0 with the next digit. So 0 plus 0 is 0, and then 0 plus 1 is 1. So this is how we get the gray code from the binary code. So this is the truth table. So we are taking 4 inputs, and of course we get 4 outputs. So B0, B1, B2, B3 are the inputs, and G0, G1, G2, G3 are the outputs. So because we have 4 inputs, so there are 16 combinations. In the blue portion we have the input, and on the right side we have the output. You can check this. I am also sharing the PDF, the link for the PDF to download the PDF in the description section of this video. You can download from it. Then in order to design this, we need 4 K maps, because there are 4 outputs, so we need 4 K maps. So the one is for G3, so we draw the K map for G3 output, and we get this. For G2 we get this part. So I have shared the link for the PDF. You can actually go there, that it is given how we get this particular equation. And for G1 we get this one, and for G0 we get this. Okay, so this is the output equation, and we can implement using the gates. So if we observe the equation, G3 equal to B3, and G2 is actually B3 XOR B2, and G1 is B2 XOR B1, and G0 is B1 XOR B0. So that is for binary to gray code converter. Now let us implement this using SimulIDE. You can use any other software. So now we are into the SimulIDE. So first we'll see how to design the binary to gray. So for that purpose, first of all we need a fixed voltage supply. So I'll just take this fixed voltage supply and rotate it clockwise. So we need actually 4 inputs. Okay, so this is one of the inputs. Just copy and paste. Just paste. We need 4, right? So we need this 4. Okay, these are the 4 inputs. Then we need actually 3 XOR gates. Of course we also need probe. I'll just take the probe here and keep it here for getting the output. 3 and the 4. These are the 4 probes. Now we need 4 XOR gates. We get the gates here. So this is the XOR gate. So 2 input XOR gate will do for us. This one, then one more XOR gate, one more XOR gate. Now the first one, let us assume this, in this case we have this particular case is G3. I can even label this. So for that purpose I'll just use this text. Okay, that's the text I'm using. I'll just double click here, and I can name this text as B3. Okay, so because B is our input, so B and 3. Okay, the same way you can actually label all this. Okay, I'll just copy it. I can just paste it so that I know what I'm connecting. I can just label it as this is B2. No. This is B1. And then of course B0. This is B0. B0. Okay. Now same way we can actually also name this. Okay, this is of course G3, G2, G1 and G0. So I'll just name this. This is G3, the output G3. So this is actually G3, and here way this is G2. This is G2. This is of course G1. G1, and then we will have G0. This is G0. Okay. So now let us do the connections for G3 is equal to B3. So this G3 is equal to B3, and the second is B2 XOR B3. So this is B2. Sorry. This is B2 XOR B3. This is B3. Then next is B1 XOR B2. B1 XOR B2. And then finally B2 XOR B1. So this is B2 B1 XOR B0. Sorry, this, and this one goes here. So just check the connection, please. Okay. Now let us verify the table. We have to connect the output also. This is the output. This is the output. This is the output. Okay. Now let us verify the outputs. So I just turn it on. So 0 0 0 is 0. Then 0 0 0 1 is of course 1. Okay. Then 0 0 1 0 is 1 1. Okay. Then next is 1 1. Okay. Now 1 1 is this what we are getting. Okay. So this 0 1 0 0. So we can verify all the 16 inputs and check verify the outputs. So this is for binary to gray. Okay. Now let us go for the next one. Now next is gray to binary code converter. So first of all, let us understand the conversion process. So if we have the gray code as 1001, then how to find the binary code of that? So what we begin is we begin with the leftmost bit 1. So we write 1 as it is, and then to find the next bit, what we do is what we got output as 1. We add this 1 with 0 next bit, and 1 plus 0 is of course 1. So next bit is 1. Now to get the next bit, we multiply. We actually add this 1 with the next bit 0. So 1 plus 0 is 1, and then 1 plus 1, the next bit is 0 carry 1. So we discard the carry and we write the sum as 0. So this is the output. You can go back and again understand this particular conversion. So this is what we get. Next, this is the truth table. So on the left side we have the inputs G0, G1, G2, G3, the gray code inputs, and on the right side we have the outputs B0, B1, B2, B3. So there are 4 inputs, so we have 16 combinations, and this is what output we get. So in order to design the circuit, we need to draw we need to actually get 4 K maps each for the output bits. So now next is gray to binary. So we require the same components, so I have taken this to save time. So first is G3 is directly connected to B3. So this is what we get. Okay. Now next B2 is G2 XOR G3. So this is G3 and G2 XORing. Okay. Now next what we have is it is G1 XOR G2 XOR G3. Now this output is already what we are getting is G3 XOR G2. So this output we get here. Okay, you can check the circuit. So this is we are getting this, and here this comes from G1. Then again this output will come here as the input to this one, and this one will get connected here, and we simply just connect this output. You can connect it from here itself. Okay, directly. It only possible to connect from this side. So this we connect. Now we can check this working. Okay, so let us start. So 0 0 0 is of course 0. We make it as 1. Of course we get it 1 as expected. Now 1 0 is 0 0 1 0 is this is 1 1. We make it as 1 1. We get this one. Okay, for 1 0 we get all as 1 1 1. Okay, so this you can verify all the inputs, so we can apply all the inputs from all zeros to all ones and verify this output. So this completes the next part, that is the gray to binary converter. Now let us go to the next part. So these are the 4K maps. For B3 we have this. So when we see the solve the K map, we get octet. So B3 equal to G3. For B2 we have two quads. So this is the equation when we solve it. So I have solved it in the PDF. The link I have shared in the description section. You can see that. Then for B1 we have this. When we solve, of course we are getting actually 4 pairs, but when we solve we get this as G1 XOR G2 XOR G3. And for B0 we have this when we solve G0 XOR G1 XOR G2 XOR G3. And this is the final logic diagram we have. We can verify the working using this particular circuit and using any of the simulator. I am using SimulIDE. You can use any other simulator. Now next is gray to binary. So we require the same components, so I have taken this to save time. So first is G3 is directly connected to B3. So this is what we get. Okay. Now next B2 is G2 XOR G3. So this is G3 and G2 XORing. Okay. Now next what we have is it is G1 XOR G2 XOR G3. Now this output is already what we are getting is G3 XOR G2. So this output we get here. Okay, you can check the circuit. So this is we are getting this, and here this comes from G1. Then again this output will come here as the input to this one, and this one will get connected here, and we simply just connect this output. You can connect it from here itself. Okay, directly. It only possible to connect from this side, so this we connect. Now we can check this working. Okay, so let us start. So 0 0 0 is of course 0. We make it as 1, of course we get it 1 as expected. Now 1 0 is 0 0 1 0 is, this is 1 1. We make it as 1 1, we get this one. Okay, for 1 0 1 0 0 we get all as 1 1 1. Okay, so this you can verify all the inputs, so we can apply all the inputs from all zeros to all ones and verify this output. So this completes the next part, that is the gray to binary converter. Now let us go to the next part. Next is binary to BCD converter. So before jumping to binary to BCD conversion, we must know the rules. The first is that if the binary number is less than or equal to 9, the binary and the BCD representations are the same. And if the binary number is greater than 9, then we need to add a binary 6, that is 0 1 1 0, to convert into a valid BCD. Otherwise we will get an invalid BCD digit. So if this is the BCD code 1001, so because this is actually a number which is less than which is actually 9, so the same we get the same BCD code. Okay, 1 for 1, 0 for 0, 0 for 0, and 1 1. So there is no change. So same BCD and same binary code. Then suppose if we take a case where we have a binary code which is more than 9. So of course here to get the BCD code we need to add 6 1 1 0. So let us see what we get after addition. So 1 plus 0 is 1. 1 plus 1 is 0, carry 1. So 1 plus 0 is 1. 1 plus 1 again 0, carry 1. And 1 plus 1 is 0, carry 1. So this carry 1 leftmost becomes the 5th bit. Okay. So in our truth table we will have 4 inputs and 5 outputs. So this is the truth table. You can see the inputs are B0, B1, B2, B3, and the outputs are D0, D1, D2, D3, and D4. So we have, in this case we need 5 K maps to get the output. So the leftmost we have this D4 for the K map for D4. This is the, we get the solution. So there are 2 chords. For D3 we have a pair, and this is the equation for the pair. For D2 we have 2 chords, and this is the equation for the 2 chords. For D1 we have a chord and a pair, and this is the equation for that. And finally for D0 we have, this is the K map, and this is the, what we get is we get an octet, and this is the equation D0 equal to B0. And this is the final circuit logic diagram. So here we have the logic diagram. The up is D4, D2, D1, D0. So there are 5 outputs actually. Now let us implement it using the simulator. Now to implement the circuit, we are into the SimulIDE. So I have already taken the inputs B0, B1, B2, B3 as previously we had taken for the other cases, and here we have 4 outputs D0, D1, D2, D3, D4. Now the difference in this case is that we also need negate that is like in this case we need negative literals, like we need B10, B0, in some case B3 bar, B1 bar, B2 bar, etc. So for that purpose we need to select a NOT gate. Okay, so I'll just take a buffer and invert this buffer so it becomes a NOT gate. Okay, and then rotate it clockwise and place it here. Similarly, I just copy it and paste it here because I need B3 bar, B2 bar, etc. So for this we need a NOT gate. So after selecting this, what we do is we do a connection from this input here. So this line will give us B3 bar and this is B3. Similarly, this is B2 and the output which is coming from this NOT gate is B2 bar, and this is of course B1 bar and B and B0 and B0 bar. So let us select with D4. So for D4 we require 2 AND gates and 1 OR gate. So just take this AND gate here, place it here, second AND gate, and then finally we need a OR gate. So this is the OR gate. So for the first AND gate the input is B2 B3, simple. So this is B2 and this is B3. So sometimes we get this. Okay, so B2 B3, and the next one is B1 B3. So this is B1 and this is B3, and this output goes to the OR gate. This also goes to the OR gate, and here this is the output. So this is for D4. Now for D3 we require a single AND gate which is actually 3 input. So I'll just take this, make it 3 input. So first input is from B1 bar. Now just see what B1 bar. So this is the B1 bar, and then B2 bar. So this is where we get B2 bar, and then finally B3. So this is B3. Then for D2 we require again 2 AND gates. Just put it AND gate here, the second AND gate, and then an OR gate. So the input is coming from B2 B3 bar, the first one. So this is B2 and B3 bar. So this is B3 bar. Then B1 B2. So we have this is B1, sorry. So this is B1 and finally B3. This is B3. Sorry, it is B1 B2. Sorry, it is B1 B2. B1 B2. This is B2. Then this will get connected here, and this will connect it here, and then of course I have to connect the output, and then this is the output. Now finally we have D1. For D1 again we need an AND gate, 2 AND gates actually. One is 3 input, one other is 2 input. So I just make it 3 input, and then we need a OR gate. So for this D1 we have B1 B3 bar. So this is B1 and B3 bar. This is B3 bar. Then this has become 4. Sorry, we need 3 actually. So 3 input. So B1 bar. This is B1 bar. First is B1 bar. This is B1 bar. then B2 B3. So this is B2 and B3, and this is connected here, and this is connected here, and finally this one. Now in the last case we just need to connect B0. We can directly connect this B0, or in the diagram, because we have written this, I have given this as AND gate. I use AND gate, so let me use this, or we can even directly connect this. So this is B0, so we connect this B0 here. Okay, so this is the connection done. Now let us check the output. So you can just open up the table. Okay, I'll just run it. So for all 0 0 0 we are having 0 0 0 0. Let us make it 0 0 0 1. We are getting 0 0 0 1. Okay, and then for 0 0 1 we are getting 0 0 1 1. For 1 1 1 we are getting 1 1 1. Now what happens if we change the input to 1 0 0 1? So we are getting 1 0 0 1. Now for, let us take one input which is more than 9. So this is 1 0 1 0. So 1 0 1 0 is 10. For that 10, this is 1 and 0 0. So this 4 digits, they represent 0, and this is 1. So 1 0. Okay. Now for 11, let us see what happens for 11. So this is 1 0 1 0. Okay. If we have this 1 0 0 1, so this is 1 1. Okay, this entire is 1 and this is 1. So 1 1 is 11. So this 1 0 1 1 is binary 11, and this is BCD 11. Okay, so we can actually verify all this. So this 1 1 1 is 15, and we get this. So this is 1, and 0 1 0 1. Sorry, this is what we are getting, 0 1 0. It is actually 5. So 1 5 is 15. So this is how we can verify all the inputs starting from 0 0 0 to all 1 1 1 1 and verify these outputs. So now let us do the last part. Now the last one is, we have the binary to access3 code converter. So what the rule is, we add a binary 3 to the given binary number. So if there are two numbers, in case we have two numbers, then we need to add binary 3 to each and every digit. So suppose we take an example. Let us take an example like we have binary code as 1001. So we need to find the access3 code. So we add this 0011, which is actually 3, binary 3. So 1 plus 1 is 0, carry 1. Then again 1 plus 0 is 1. Then 1 plus 1 is 0, carry 1. So this is 1. 1 plus 0 is 1. 1 plus 0 is again 1. So we get this 1 here. Then finally 1 plus 0 is 1. So this is the output we are getting for access3, 1 1 0 0 for 1 0 0 1. Now let us see the truth table. Okay, so this is the truth table. Now in this truth table there are 4 inputs and 4 outputs. The last 3 outputs, as we can see, they are XX. So that means a don't care condition. So don't care conditions are those conditions we don't care what output we are getting for the given input conditions. So the last 3 conditions, if we see the third last, we have 1 1 0 1. If we add 1 1 to it, then we get an overflow. It would require more number of bits, but we only have 4 bits. Therefore in the last 3 cases, we are getting an overflow. So we are actually replacing that by X, that is a don't care condition. So these are the conditions. So you can see this is 1 1 0 1 1 0 1, we are having a don't care, and for the last 2 also we are having the don't care conditions. Now let us draw the K map. So there are 4 K map 4s, one for E3. So there is a octet and a quad. For E2 we have 2 quads and a pair, and for E1 we have 2 quads, and this is the equation, and for E0 we have an octet. So you can see this is the output. Okay, the logic diagram, we can verify this using any of the simulator. So let us now verify it using the simulator. So now we come to the last conversion from binary to access3. So I've already done with the circuit. As you can see, I've already drawn this, I already traced this. So to save time, you can do this carefully. For E3 we have B3 or B1 B2. So this is what we are having. Then for E2 we need 3 AND gates and final OR gate. And for E1 we require XNOR gate. This is an XNOR gate. Okay, so when we select, we have XOR, so we need to invert the output, so it becomes XOR. And finally we have E0 equal to B0 bar. So this I would selected AND gate. We could have directly connected this to the probe, but I've selected an AND gate. So we have one gate. Now let us verify the circuit. So let us start it. So all the inputs are 0 0 0 0. So 0 0 0 0 plus 3 is, we get 0 0 1 1. So what is we are getting? 0 0 1 1. So this particular adder, it adds 3. This particular code, it adds 3 to the binary code. So suppose if we make this as 0 0 1, so it becomes 1 0 1 0 0. So this is 1, this becomes 4. If we make this as 3, this becomes 6, as you can verify. So we can actually give all the inputs, all the possible combinations from 0 0 0 0 and to up to 1 1 1 1, and then verify this. So you can use the truth table and verify the readings. When all are 0, what we are getting? E0, E1, E2, E3, etc. So that's all for this particular session. Thanks for watching. Do join us for the next video.